Section 1.2 describes different types of data. These are different ways that we can categorize data. You might call them dimensions of categorizing them. So the three main categories that we'll talk about today will be statistics versus parameters, qualitative versus quantitative data, and then we can talk quite a bit more about quantitative data because it can get subdivided into other dimensions. So let's start out by talking about the definitions of statistics and parameters. Let's go ahead and review something we talked about in section 1.1, which is the difference between a population and a sample. Remember that a population is the entire body of interest that we'd like to learn about, and the sample is the part of it that we're actually able to observe. So the data that describes these two bodies, the whole population and the sample, have different names. Numbers that describe the whole population are called parameters, and numbers that describe the sample are called statistics. That's very convenient because doesn't that make a good memory device? You can think about the letter P, population, parameters, and then the letter S stands for sample and statistics. Technically speaking, the statistics are really the only data that we have because remember, we can't observe the whole population. We really can only make educated guesses about the parameters. So in my book, technically speaking, parameters aren't really data, the way I defined it the other day, because data is something that we observe, and we really only observe the sample. But that's kind of picking a nit, I think. A parameter, in any event, is some number that describes the population. Like the two most common and basic types of parameters or statistics that we'll learn in this class will be means and proportions. So let's just say, let's talk about a mean, for example. Let's suppose that this population represents all blue scrub jays in North America. And we're interested in finding out how long their beaks are. So theoretically or hypothetically, if we could gather all the blue scrub jays together in North America and measure all their beaks, we should objectively be able to find that they have some average. You know, whatever, 2.1 centimeters it might be. That might be a number that, well, it's a number that it's a true number that measures the whole population, although no human would ever really know it. So the population has its mean, and then let's suppose that we take a sample of 2,000 blue scrub jays and take measurements of their beaks, and then we can average those 2,000, and we might get a mean of 2.3 centimeters. And that would be our statistic. Now, they're both means, aren't they? So let's not be confused and think that only a population has a mean or that only a sample has a mean. They both have means. And they're usually not going to be the exact same number either. But the parameter, theoretically speaking, is one number that is, if you want to think about it this way, it's only known in the mind of God, right? And the statistics are the numbers that we actually observe, but both of those can be means or proportions, for example. Okay, let's talk about the next issue. So again, here to wrap this part up, we usually use statistics to make educated guesses about parameters. That's a central theme in this class. Okay, so some data is what we call qualitative and other data is called quantitative. This is just derived from the words qualities and quantities. Quantitative data takes the form of quantities, numbers. And these are usually used to measure or count things. So if in the last example, when we are measuring the length of scrub jays' beaks, that would be quantitative data, wouldn't it? Because we can measure a beak as like 2.3 centimeters. Qualitative data would be anything that takes a non-numeric form, like names or categories. For example, blue scrub jay. So you might have a list. You might go out into the field and do some bird watching and kind of write down all the different species of birds you see. I see some blue scrub jays, I see some wrens, I see some hummingbirds, I see some bald eagles. And you would have a list of data there, but each data entry would just be like a name or a category of a species. So that's qualitative data. Pretty simple distinction. Now, quantitative data is more interesting, perhaps. It's more complex, and obviously we're going to spend more time on it in this class. So let's do a further breakdown of how we could categorize quantitative data only. And there are two main issues that we want to discuss here. One of them is that some quantitative data is continuous and some quantitative data is discrete. And then after that discussion, we will talk about different levels of measurement that, again, really only apply to quantitative data. So let's start with the question of continuous versus discrete. All right, so I think the best way to visualize the difference between discrete data and continuous data is looking at a number line. Discrete data would be something that we could only measure as points on a number line. For example, if we ask the question, how many children do you have? The possible answers could be 0, 1, 2, 3, 4, and so on. But it would never be 2.8 or -3 or 1.5. The possible answers are separate and distinct points on the number line. And a discrete data question is often triggered by the word many, the phrase how many children do you have, as opposed to how much gasoline is in your tank. That would be continuous data. So if you look for English cues, you would never say how much children do you have or how many gasolines do you have, right? So that's a pretty good pointer for the difference between these. So continuous data, like the amount of gasoline in your tank, can span any point on a continuous interval on the number line. And that's usually represented by just shading continuously like a spectrum from the minimum to the maximum. The amount of gasoline in your tank could be 1 gallon or 2 gallons, but it could also be 1.5, 1.5, or it could be 1.3, or it could be 1.27184. You can basically put as many decimal digits in there as you want. And as you're filling your tank, it will flow continuously from empty to full. And then the final issue, and again, this applies only to quantitative data, is levels of measurement. Now remember, quantitative data is measured by numbers. It's identified by numbers, but some numbers are more strongly numeric than others. So that's really what the level of measurement comes down to. It answers the question, how strongly numerical are the numbers that we're using to represent this data? And on a scale from weak to strong, there are 4 categories. They're called nominal, ordinal, interval, and ratio. And I think the best way to understand this is to begin with nominal, and then as we progress, we'll talk about what each level has that the previous one doesn't. So nominal data is numbers in name only. So for example, you might be taking some data on the colors of marker pens, right? Some of them are black, some of them are red, some are blue, and some are green. Well, if you want to enter this into a computer, you might assign these numbers, these categories numbers. You might say, well, black will be category 1, and red will be category 2, category 3, category 4. So that would be a nice way to encode your data, but those numbers are really just stand-ins for names. It wouldn't make any sense to say, well, this is category 1 and this is category 3, so they have an average of 2. It doesn't make any sense to add, subtract, multiply, or divide those numbers together. And we could just as well have switched these around. I could have said that this is category 3 and this is category 1. So there's no inherent order to it. It's just an arbitrary naming system. So when we get to ordinal data, What ordinal data has that nominal data does not is, well, I guess you can guess from the name, right? It has order. So with ordinal data, you're able to talk about quantities that are meaningfully less than or greater than others. And a really good example of ordinal data is what we call the Likert scale. I think that's how you pronounce it, which is used frequently for surveys. And the question will take a form something like, how strongly do you agree with the following policy position? Give the answer 1 if you strongly disagree. Say 2 if you disagree. Say 3 if you're neutral. 4, agree. 5, strongly agree. So when you look at a survey like that, there's something about a 4 that's greater than a 2. It means that this person really has stronger feelings about agreeing with something. Okay, now what does interval data have that ordinal data does not? And the way I like to answer this question is that interval data has a meaningful unit of measurement. So if you think about that Likert scale, if you answered 4 to a statement, yes, I agree with it, I give it a 4, well, that 4 doesn't really measure anything, does it? You can't say 4 what? 4 pounds, 4 gallons, 4 degrees Fahrenheit? No, just 4. It's just a number on a scale. But if I ask you for the temperature in this room, you might say, oh, it's 72. 72 what? 72 degrees Fahrenheit. Oh, okay. So that has a meaningful unit of measurement, a fixed unit of measurement. And basically, when you have fixed units of measurement like that, not only is there an order to it, but you can also add or subtract them. So you could say, well, it was 72. It's 72 degrees Fahrenheit in the room today, and it was only 68 degrees yesterday. So if I subtract those, there's a 4-degree difference. So that wouldn't make any sense on the Likert scale, would it? But it does on the interval scale. All right, and then finally, there's the ratio, which is the strongest level of measurement. And I think that students who are new to this are usually most puzzled by the difference between interval and ratio data. To make things a little bit easy, there are really only 2 common forms of interval data, and they are degrees of temperature and year numbers. So this is the year 2024. In 10 years, it will be 2034. That's another interval scale. What ratio data has that interval data does not is, that might strike you as kind of weird, but it has an absolute 0. In other words, when the number is 0, that really means that there is none of what you're measuring. And again, I know that this concept is a little bit slippery, but when in doubt, interval data really only applies to temperature scales and year numbers. But think about something else like how much something weighs. How much does this watermelon weigh? Well, if I say 0, that really means there is no watermelon there. It means nothing. Whereas if I say it's 0 degrees Fahrenheit, well, you can get lower than 0 Fahrenheit. So 0 in that case doesn't really mean nothing. It's just kind of an arbitrary point on the scale. But most measurements that we're interested in taking physically do have an absolute 0. When you have $0, it means you have no money. When you weigh 0 pounds, it means there is no weight. If you are 0 years old, it means you were just born. Okay. And the mathematical advantage of ratio scales is that you can not only multiply and subtract them, but you can also, you not only add and subtract them, but you can also multiply and divide them. So if one watermelon weighs 10 pounds and another one weighs 5 pounds, the first one weighs twice as much as the second one. Okay, got to get going. I need to limit these videos to 15 minutes, and I'll see you in the next section.